Hello again. In this video, we're going to be talking about the practical application of the combination of a positive thermal expansion and negative thermal expansion material developed in the previous video. So in this case, we have aluminum and ALLVAR. And if we're interested in creating, for example, 0 CTE, this doesn't necessarily need to be 0, it can be any constant. But 0 seems to be quite popular for stability's sake, which is important. And you start to combine aluminum, this is the strain versus temperature, negative 40 degrees C to 80 degrees C. And if you look at aluminum 6061 with a T6 heat treatment, you see that it increases with increasing temperature, and the ALLVAR Alloy 30 does the opposite. You'll also notice that the ALLVAR Alloy 30 has a curvature to it, whereas the aluminum 6061 is very straight, and we'll actually get into the implications of that curvature versus that straight line. And so when we combine a positive thermal expansion aluminum and a negative thermal expansion ALLVAR, we have the equation we developed to understand how long the ALLVAR piece of material needs to be compared to the total length of the beam, and that is equal to alpha total minus alpha aluminum divided by alpha ALLVAR minus alpha aluminum. So if we want 0 coefficient of thermal expansion, this term goes to 0, and we're left with negative alpha aluminum divided by alpha ALLVAR minus alpha aluminum. So if we want 0 coefficient of thermal expansion, it's the simple ratio of the the aluminum thermal expansion divided by the difference between the ALLVAR and the aluminum coefficients of thermal expansion. So in the previous video, we developed this for the thermal expansion coefficient, or the average thermal expansion coefficient. And it kind of brings up a question. Well, what is temperature 1 for the average coefficient of thermal expansion? Well, the average coefficient of thermal expansion is given across a temperature range. So if you had a temperature range, for example, from negative 40 to plus 80, your T1, or your reference temperature, is going to be equal to your low temperature plus your high temperature divided by 2. It's effectively the average of your temperature extremes. And in this case, if you have negative 40 degrees C plus 80 degrees C divided by 2, you're looking at 20 degrees C, which is halfway between negative 40 and 80 degrees Celsius. So if I were to take the average thermal expansion for these two alloys between negative 40 and 80, we can look at what this equation would come out to. So this ratio of ALLVAR to the total length at T1 equal to 20 degrees C is equal to negative 22.3 times 10 to the negative 6 divided by negative 30.2 times 10 to the negative 6 minus 22.3 times 10 to the negative 6. And the average CTE, if you don't remember, you take the strain at one temperature, at your lower temperature extreme, the strain at the upper temperature extreme, you draw a straight line, and that slope of that straight line is equal to your average CTE. So this is the average CTE from negative 40 to 80 degrees C of ALLVAR Alloy 30, which is negative 30.2. This is real data from a real piece of material, and so it's not exactly 30, but it gives you that ballpark range, which is really good. So so this is true actual data collected on these materials. And what you see is for this piece of ALLVAR and this piece of aluminum that was tested, you get an L1 ALLVAR divided by L total of 0.42. So if you have, let's say, a 1 meter long piece of material, 0.42 meters will be ALLVAR, and the balance will be aluminum to achieve zero coefficient of average coefficient of thermal expansion from -40 to +80. But this curvature that the ALLVAR Alloy 30 has can make it to where the extreme temperatures will experience differences in strain. So if you actually take the average CTE, or you take this ratio and you actually put it into the strain values, you see that the strain versus temperature will look something like this. And this is for L1 ALLVAR divided by L1 total at T1 equals to 20 degrees C is equal to 0.42. And this would be for alpha average. So this is the average thermal expansion. You see that at the extremes there's going to be a shrinking over here and a shrinking down here, and at 20 degrees C it'll be 0 CTE, which is the slope of this curve. And that discrepancy at the extreme temperatures is due to the curvature compared to the straight line of the ALLVAR Alloy 30 compared to the aluminum 6061. But this curvature can give us almost a hidden or a secret weapon. So what happens is, if we take a look at the instantaneous CTE and use this equation, I know it was developed for average CTE, but what happens when we start to use the instantaneous CTE? What we see here that T1 is equal to a constant value, a single temperature. And we can start to use this CTE, this unique curvature, to dial in where the CTE is. So if I wanted to set alpha total instantaneous to equal to zero at T1 equal to 20 degrees Celsius, then I would use L1 ALLVAR divided by L1 total and use the instantaneous CTE instead of the average CTE here. And it comes out to something quite similar. So in this case, the instantaneous CTE at 20 degrees Celsius for aluminum is 23.4 times 10 to the negative 6 divided by ALLVAR being negative 29.8 times 10 to the negative 6 minus 23.4 times 10 to the negative 6. And if you calculate that out, it comes to 0.43. So in this instance, the average CTE and the instantaneous CTE for 0 CTE at room temperature is quite similar, 0.42 versus 0.43. And if we take a look at the instantaneous CTE versus temperature, this being aluminum 6061, and this being ALLVAR Alloy 30, we see that these two produce a curve, an instantaneous CTE curve that looks something like this, where this is alpha total. So that's an effective CTE of this total bar. Now, here's where the interesting thing comes in. Because the ALLVAR CTE is changing with temperature, we can actually create a zero CTE at crossing, a zero instantaneous CTE crossing at any temperature that we want. So for example, if I want the total coefficient of thermal expansion to be 0 at T1 equal to negative 40 degrees Celsius, what I need to do is take L1 ALLVAR at negative 40 degrees C divided by L1 total at negative 40 degrees C. Notice you actually have to measure these at the low temperature. But what that gives you is negative 21.4 times 10 to the negative 6. So that's the instantaneous CTE. This is negative 40. It's the instantaneous CTE of the aluminum 6061 at negative 40 degrees Celsius. You divide that by negative 23.4 times 10 to the negative 6. And then you subtract the aluminum's coefficient of thermal expansion as well, times 10 to the negative 6. And that is equal to 0.48. So by adding a little bit more aluminum, what you get is an instantaneous CTE curve that looks something like this, where your 0 point CTE crossing is at negative 40 degrees Celsius instead of 20 degrees Celsius. So this would be alpha total set to at T equals negative 40 is equal to 0. So now you can actually, if you added a little bit less, or you add a little bit more aluminum, took away some of the ALLVAR, then you can actually get this 0 CT crossing to increase in temperature. So you can actually dial it in across a very wide temperature range. And this can be important if you're not concerned about very large temperature swings, but if you're concerned about smaller temperature swings, maybe plus or minus 10 or 20 degrees Celsius, where this discrepancy between that's caused by the curvature at the extreme temperatures isn't that big of a deal. And you can actually dial it in to whatever the operating temperature of the system you're working with is going to be working at. So this is a really exciting and interesting thing that you can do with ALLVAR that you can't do with any other material because it doesn't have the curvature and it doesn't have the negative thermal expansion coefficient.